let's begin. Okay, so we have a problem which I sort of skipped over before because the timing wasn't right. So here we are, finishing it off. And in fact, we're going to finish off the rest of this stuff from packet 1 today, and move on to packet 2 on Wednesday. So and some of the stuff that's in here might be useful for your current assignment. I apologize I haven't got to all of it, but some of you have attempted some problems and received some a little bit of headwind. Okay, so hopefully this will clear up the things that you're missing. Anyway, a problem. Okay, so arranging digits. Okay, so how many 5-digit numbers are there which contain at least one zero? It's just a bit of note about what it means to be a number versus a string. We've seen strings before. Strings can just be, they're just like compositions of characters, and when we talk about binary strings, the characters are zeros and ones. They are not numbers, okay? So you have to have something in each place. A number, when you write a number in a natural sense, you tend to trim off the leading zeros. Okay, so if you have a 5-digit number, it can't be like 0, 0, 1, 2, 3. It can't be something like that. Okay, so there are no leading zeros. That would be 1, 2, 3, which would make it not a 5-digit number. The only number that begins with a 0 is 0, and it's a 1-digit number. Okay, so zeros can appear elsewhere. Okay, so in any of the 4 other positions, they can occur. Okay, so I've written or got a solution started. Okay, so let's just talk about the solution. Okay, so a 0 can't appear in the first spot, but it could appear in any of the other 4 spots. Okay, so it could be in the second spot, or the third, or the fourth, or the fifth. Okay, so this or will sort of lead to a rule of sum type of deal. Okay, so a rule of sum. Okay, so this is basically case A, and in case A, the first digit can't be a 0, so it's 1 through 9, there are 9 choices. And in these ones, it's 0 through 9. Okay, so 10 choices, so 9 times 10 times 10 times 10 gets you 9 times 10 to the 3. Case B looks like this, so the 0 is here. Again, it's like 1 through 9, 0 through 9 for the other ones, right? Okay, and again, you end up with 9 times 10 times 10 times 10. So case C ends up with something similar. 9 times 10 times 10 times 10. Case D, something similar. Okay, and there are 4 cases. Okay, so we will eventually add these things together. Okay, and they're all the same, right? Four of these things. So it's like 4, it's sort of like there's a 4 times 9 times 10 to the 3 in there. But, you can do the addition. That's fine. Okay, and you get 36,000 numbers. Okay, of, I guess, 90,000 possible, yeah? What do you mean? Where do they overlap? Good, yeah. Okay, so the problem here is that we can't just use the rule of sum like this. Okay, the rule of sum requires things to be distinct. Okay, they don't overlap. I guess I said disjoint. Okay, so they don't overlap. And you gave a good counterexample. Case A and case B overlap when there are zeros in these 2 positions. You gave the example of 10,000. Actually, all 4 of those overlap in that case. Okay, so this is the wrong approach. Okay, so why? Because the cases overlap when there are multiple zeros. Okay, and that ends up giving us an overcounting, okay, because some of these cases have been counted twice, or 3 times, or 4 times, depending on how many zeros are in there. Okay, and it's not so simple like as to use inclusion-exclusion, because there are 4 cases here, A, B, C, D. You could do the 4-case inclusion-exclusion rule and sort of, undercount, overcount, sort of do the alternating adding and subtraction, but you would need to deal with not just these 4 cases, but I guess 11 others, okay, wherever these things intersect. Okay, that might be a fair amount of work. But this number here is definitely an upper bound. Okay, so as an estimate goes, as a sanity check, we'll see when we actually give the right solution if we are at least bounded above by this. Okay, I don't know how much of an overcounting that is yet, okay, but I need a solution from you. Okay, so how should we count this? How would you approach this problem? Okay. Okay. And divide by. So if you take all the possible combinations of things that are possible here, you get 90,000, right? So you get 1 through 9 is 9, and then 10 times 10 times 10 times 10. You get 90,000. I don't know that there's a clean way of dividing by a number, because I don't know where the duplicated cases are, and it might not be obvious, but some cases are counted like twice, 3 times, and so on for the zeros. Okay, so we need to get the at least 1 0 thing in there as well. We'll come back. Yeah. Okay, I like that. So your strategy is look at where the first 0 ought to come. Okay, so that's good. All right, so solution B. Do 4 cases, but by where the first 0 occurs. I like it. Okay, so case A, would have, okay, so there's a blank and then 0, blank, blank, blank. The first one is going to be 1 through 9, and then the rest of them are unrestricted. Okay, so that one doesn't change. But case B, your first 0 will be here. So these first two are guaranteed to be 1 through 9, and then these ones are 0 through 9. I like it. I think that works, right? That makes sure that they're not overlapping, right? Sorry, I'll get it up there. Okay, so blank, 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 0, blank. So this is, it's basically 9, 9, 9, 10. Case D, 0 occurs in the last one here, so that'd be 9, 9, 9. Okay, I like that. Okay, so this is, by the rule product, this is 9 times 10 to the 3, so that's our 9,000. This one is 9 squared times 10 squared, that I can do in my head, 8,100. This one is 9 to the 3 times 10. 9 to the 3 is 729, so 7290. And then we have 9 to the 4. That one I can't do in my head. What's 9 to the 4? Nobody has a calculator? Okay. It's a mystery. Let's see, 729 times 9. 6561? Okay, so by the rule of sum, this is 9,000 plus 8,100 plus, okay, so let's just do the adding by columns here. So there's a 1, and there's a 5, 9, 30,951. Okay, and we compare that with the 36,000 that's sitting up there. Okay, so it's bounded about, that's how much we were overcounting by, and it's not clear that it's going to be like, whatever that is, 4,049? It's 5,049? 5,049? Seems a little bit strange. Okay, anyone else have a way of going about this problem? I think there's more than one solution. It's often the case with combinatorics. There's more than one way to look at a problem. Anyone come up with anything else? Okay. Oh, I see. So you're placing the zeros in various locations. That will end up with a long list of different cases, but yeah, there might be a more efficient way so just to riff off of that a little bit. You could choose the positions of the zeros and say, okay, well, if there are, say, 2 zeros, much like we had 2 6s in the dice rolling example, we basically select where the 2 zeros go, right? And that might save you, like, writing 6 lines for the 2 zeros cases, right? And then you could do, like, by number of zeros, like 1 0, 2 zeros, 3 zeros, 4 zeros, so you'd only have 4 cases that way. Yeah, that might be a little bit more efficient, yeah. Okay, so solution, I'm not going to write this one out. Okay, solution C would be cases by number of zeros. And there will be 4 of them. Okay, so you'll do it like the dice rolling example where you're counting the 6s. Any other solutions? I saw another hand or two. Maybe that was the same one. No? Okay, so one other way that you can approach this thing is by counting backwards. And okay, so use subtraction. You can take the whole number of cases, which is 90,000, okay, so that's without restrictions, and subtract off the cases where there are no zeros, which is actually really easy to count, right? It's 9 to the 5. So that would hopefully, let me try that right now. So this is 9 times 10 to the 4 minus 9 to the 5. That I can do, 90,000 I can do in my head. What's 9 to the 5? What's 9 to the 5? Say that again, 5? 59049. Yeah, that seems to match. That's good. Okay, so as a sanity check, that seems to be another method that works. Okay, so sometimes it's cleaner to do it that way, and you can look at the thing that you're not trying to count and use the complement rule on that. Okay, let's do a little review. Yeah. Okay, so we've, mostly it's been review, right? This combinatoric stuff. If it's all brand new, I'm sorry, it was a bit of an uphill climb, but hopefully your first assignment or assignment and a half will get you going on combinatorics and practice. There are lots of practice problems out there. Most of them give you practice in dealing with these 3 main generalizations, which I'll get to in a second, but it's usually, applying one of those formulas or breaking it up into cases or counting backwards into one of these 3 generalizations. Anyway, the main things, the first principles are the rule of product and the rule of sum. Okay, so breaking things up into cases, you end up hearing an or in your head when you redescribe the problem, so you add. Okay, and sometimes there's an overlap, you might have to do inclusion exclusion. If you hear an and, so there's an event followed by another event, then you can multiply the cases together, you end up getting this rule of product thing. Okay, so adding and multiplying, these are 2 very familiar things. And we saw some generalizations of, ordering things. I always like to think of a bag of things that we're sort of sampling out of. I know it's sort of weird to think of putting people in a bag, but anyway, whatever. So you take the thing out of the bag, you put it in a line, and then you either put it back in the bag or you leave it out of the bag. You can have duplicates or you can't. Okay, so those are the first generalizations that we came up with. One was this with replacement idea, and the other is without replacement. When it's with replacement, it's just n times n times n times n, and when it's without replacement, the number of things in the bag goes down by 1 at every time, and it ends up giving you something that looks like a factorial. Okay, so n times n minus 1 times n minus 2, and so on. If order is not important, and this is an interesting thing, you get selection. This is a choose, and you end up dividing by another r factorial from this to this, permutations to combinations. Okay, and it's up to you. Oftentimes, this is the hardest part of the problem, is deciding whether order matters. Okay, so you will often choose between these two things. Anyway, these three generalizations are very useful. And some other techniques, one is to use subtraction. So you might intentionally overcount with the idea that you're going to subtract off this stuff later. One might be to count backwards, just like I suggested in solution B just now. That would be the complement rule. Okay, the other is that you can't actually use the rule of sum. A and B overlap, so you use inclusion, exclusion, subtract off the difference. Okay, the other way is you're overcounting by a factor. There are k cases for every one case that you want, so you know how to count the one thing, you divide by k to get the final answer. Okay, so that's all the stuff that you've learned so far, and notice that everything here, you're all unique individuals, right? Okay, you're all distinguishable objects from each other. It's all that kind of case. For the rest of today, I'm going to show you what happens when you need to count things where they're the same object. Okay, they're indistinguishable from each other, and once you've done that, then that will be it. That will be it for combinatorics. Okay, let's do it. Okay, first problem will be an anagram problem. So what is an anagram? Man, a lot of people have made their scratch by making anagram-style apps on the internet. Okay, so word games. A lot of word games are anagram things. Okay, scramble up the letters and make other words. That's what an anagram is. And this is, a word in the purest sense. Okay, so in the mathematical sense, a word is just a composition of characters, and it doesn't have to make actual sense as an English word. Okay, so if we look at the number of anagrams of seat, there are 4 ways of putting it in the first slot, first character, and then that letter can't be in the second slot, but there are 3 choices remaining for that, times 2 times 1. This is 4 factorial. And of course, it's only an interesting game because, you want to try to find the actual English words that come out of these. Should we do that? Should we do that for seat? Yeah, let's have some fun, eh? Give me an anagram of seat that's actually an English word. Eats. Good. Haze. Don't go to Vancouver Airport. Oh, sorry, too soon? Yeah. Sate. Oh, I see, like that one. Nice, without the E, like your breakfast teas, yeah. East. We're not done. That's not a word. Yeah, you don't H the sandbox, right? Yeah. Sorry, that's not one of them. See who's a Scrabble player here. Really, that's it? That's all you got? There's 3 more. What? There's 3 more? Oh my god. You're going to say? Seat is an anagram. It's sort of a trivial anagram, but it's an anagram, right? It's like multiplying by 1, but it is one of the 24 combinations. Very good. Aset, no, not a word. You made that up. It's what? It's a company name, yeah. No? All right. I'll let you think about it. We're not gonna go on from this slide until we've finished it because we're completionists, right? We want 100% the video game. But okay, 2 more to go. Yeah, 1 more. SATA, good. I think it's some part of a plant. I think it's like a bristly thorn or some sort of part on like a plant. All right, we'll leave it for later. All right, well anyway, let's just examine part B to this problem. Okay, so there are 24 possibilities. And you know that factorials grow really rapidly, right? So if you wanted to make a video game that generated anagrams for human pleasure, it's probably okay, right? That 4 factorial is 24, 7 factorial is much bigger, and if you had even more letters, this would be a great problem for a computer to solve because it could just chug through all of those things, whereas it would be too time consuming for someone like us to design a game like that, right? To check every possible thing in the dictionary. Okay, so this lends itself really well to computerization. What about seats? How many anagrams for seats? Well, it's interesting that, there are 5 letters here and not 4 anymore. So we could just hit it with a 5 factorial. The problem is that we'll overcount. Okay, and why are we going to overcount? Well, if we were to look at these 2 S's, they're actually the same object. They have the same effect in the final word. Okay, so but they're not marked as different until I put little subscripts on there. And I'm going to show you what the overcounting is in just a second. All right. So first, let's write this down. So the same technique would yield 5 factorial anagrams, which is too many, because if we were to end up with an anagram that looks like this, okay, but we're tagging these S's now as distinct objects here, S1 and S2, we would end up with this scrambling of the 5 factorial and this scrambling of the 5 factorial. And the problem is that these two objects, they look the same once we remove the subscripts, right? So they're the same thing, and that means we overcounted. Okay, so these things, those two things are two different permutations of the 5 factorial that yield the same result. Okay, so that's one duplicate case, right? But no matter what case you take, there's always going to be a duplicate case. Okay, so if the two S's ended up at the front, you flop them, you end up with a pair, right? No matter where the two S's, here and here, okay, they flop them, they end up with. So everything is going to end up with a copy, all right? And so it's like a division rule thing again. Okay, so we're overcounting by a factor of 2. Okay, so there are 2 copies of everything. And so we use the division rule, and we would end up with 5 factorial by 2 different anagrams. Okay, so not quite 5 factorial. Okay, so 5 factorial would be 120 divided by 2, 60. Okay. Yeah, you're trying to answer the question on the next slide, but that's true. That's true. So the number of permutations of these S's is really 2 factorial. So that's where that comes from. Yeah. Okay, we have one blank here. Betas, good. Scrabble player. You gotta put the Greek things in there, right? Yeah, all right. Okay, just a little bit of fun there. So 8 of the 24 things end up with English words. All right. Yeah, next. Error. Okay, so what do we do for error? Well, there'd be 5 factorial initially, but the number of copies of duplicate things with the R's will be 6 this time, right? Right, because it's like R1, R2, and R3, and the number of ways of scrambling up, an angry line of 3 R's, right, is 3 factorial. Right? Okay, so that is the key point, and you mentioned that, I'll put it on there. Okay, because we're going to put factorials on the denominators for all of these going forward. Okay, so key point, the number of internal arrangements of the duplicated letters. Okay, in this case, 3 factorial. Okay, that is the, we have 6 copies for every one that we want to keep, right? So that is the factor that we overcounted by. Okay, so that equals the factor we should divide by. Okay, so in this case, there are going to be 5 factorial by 3 factorial, okay, anagrams. Okay, so this 3 factorial, once again, is the number of internal arrangements of the 3 R's. Yeah? Okay, next one, banana. How many ways can we scramble up banana and get an arrangement, get an anagram? Yeah. And how'd you get that? Good. Okay, so we're internally permuting the A's, you said first. Okay, so there are 3 factorial ways. But the number of permutations of the N's is also a factor. Okay, so internally permute the N's in 2 factorial ways. Okay, so we're going to divide by the product of these things, right? That is the number of duplicate arrangements that we get. We're dividing by that product. Okay, so there are 6 factorial by 3 factorial, 2 factorial anagrams. Okay, so this anagrams, all right? So we are taking a long series of characters, we take the thing on the top, the total number of objects, and then we divide by the permutation of the duplicated, the indistinguishable characters, okay, whatever they are, factorials. Okay, so there's an equivalent problem I'm going to show you now, and it has to do with partitions. Okay, so how many ways are there to partition a set into specific size bins? And the reason that this is the same problem is because, well, if you have an anagram with, so many A's and so many N's and so many B's, you can lay out the slots and sort of say, okay, well, where are the positions for the A's, right? And it's like choosing a set of position things. And so pick 2 for the A's and 3 for the N's and 1 for the B's. Okay, so it is partitioning positions where each of the set sizes is, it's the number of duplications of each character. Okay, so you have K sets, and each subset is going to have a specific known number in advance. Okay, there are 2 different solutions to this. I'll call this one solution 1. One is to do an anagram. Okay, so do it by position, and treat each of these subsets as a subset of position. Okay, so treat as an anagram with n1 ones. Okay, so they're digit strings. That's fine. Characters are characters. n2 twos, and so on. nk k's. Okay, so how many different ways are there? Well, just generalizing it from the previous page, there's n factorial, that's the total number of characters, and we divide by n1 factorial, that's the number of duplicate 1s, and n2 factorial, number of duplicate 2s, and so on, and the last factorial we have here is nk factorial. Okay, another way is to actually build the subsets, and you can do this using chooses. Okay, so solution 2. Okay, so we can build these things in turn. We can start with the elements of A1. Okay, so choose the elements of A1. And there are n elements to choose from. We're going to choose n1 of them. Okay, so in n, choose n1 ways. Okay, so we take those, drag them into the set. We have n1 fewer elements to choose from on the next step. So the next step is to choose the elements of A2. Okay, so there are n minus n1 of those elements, and we're choosing n2 of them. And I'll do one more here. Okay, so the elements of A3 in n minus n1 minus n2 choose n3 ways. And this process continues. And you use the real product and you multiply all these chooses together. Okay, now I'm going to save us a step rather than write out these chooses and then expand them. I'm just going to expand them. Okay, so this first one is n factorial by n minus n1 factorial n1 factorial. Okay, and the second one is n minus n1 factorial on the numerator, and then we end up with n minus n1 minus n2 factorial, n2 factorial. And we'll do the third one here. Okay, so the numerator here is n minus n1 minus n2 factorial divided by n minus n1 minus n2 minus n3 factorial, n3 factorial. And there are k of these things. I don't have enough paper or time to write them all out. I'll give you a moment to catch up. Okay. So if you look at what's going on here just for a moment, right, there's a lot of juicy things that I got the big thick red marker out, okay, because I love canceling things out, don't you? Oh, it feels so good. It feels so good, right? Because you have n minus n1 factorial over here and n minus n1 factorial over there. Bye-bye. And you have the same one here, n minus n1 minus n2 factorial, and this one, they also divide out. And if we did the next term, that would divide out here, and so on, all the way down the line. And the surviving bits are the n factorial on the top, and the n1 factorial, n2 factorial, and 3 factorial on the bottom. And we end up getting the same thing that we ended up here. Okay, so I'll rewrite it. Factorial, n2 factorial, and k factorial. Okay, so everything ends up canceling except for the one on the top, the first one, and these parts on the bottom. Cool, eh? Okay, so the telescoping product ends up getting us the same result as the anagram solution. I always like the anagram solution because it seems so clean, like it maps onto something that we can almost gamify in our heads. Anyway, these two things are generalizable. This sort of looks like the choose from 4, except the denominator has a whole bunch of factorials that all total n, and so their original total is n. This has a notation which is sometimes used where you do not just n, but you do n choose, n1 choose, n2 choose, n3 choose, nk. This is known as a multinomial. And I don't want to go into the discussion any more than to call it a multinomial, but there is another theorem. We talk about the binomial theorem. There's also something called a multinomial theorem that works on things like x plus y plus z to the n, right? And it will show up in there as well. Okay, so this might be useful for a problem or two in your homework. Okay, so just keep this in mind. Okay, any questions about anagrams and this partition problem before we do bananas in lunchboxes? Yeah, is it good? Oh, big red thick marker, I love it. Oh, so good. All right, last thing. I taught Macam 101 for a lot of years, and when I first started teaching Macam 101, I did the bananas in lunchboxes as the first example, and then everybody in my class started talking to the TAs and said, is it like a bananas in lunchboxes problem? And then sort of the name sort of stuck and became a life of its own. So anyway, here you are. Many years later, I'm still talking about bananas in lunchboxes. Okay? So what is bananas in lunchboxes problem? Well, we have 10 identical bananas. These are the indistinguishable objects. I know, some bananas are better than others, but for our sake here, we only care about the number of bananas that each person gets. The people are all different though. Okay, so these boxes are all going to 5 different people, and it might matter if your lunchbox has 2 bananas versus 4 bananas. You might be happier or unhappier depending. Okay, so the question is, how many different ways can this be done? And this is, the objects that we're distributing are indistinguishable. This is interesting, but how we're distributing them to is not. Okay, so what do? We recycle an old problem, and we actually do like a mapping, like a combinatorial proof in a way. And it's very clever, actually. You use binary. Okay, so you map each of the possible distribution of bananas into the lunchboxes to a binary sequence. And what's in the binary sequence? There are 10 zeros. These represent the bananas or the fruits or the objects you intend to distribute, the indistinguishable things, and 4 ones. And these represent the dividers. Okay, so I'm going to write down a binary string, and you'll see what I mean. Okay, so I got 14 characters. Two, three, four, five. Okay, I got 10 zeros in there. Perfect. Okay, so how do we read what is going on with the bananas in the boxes? Well, the dividers actually represent the division points between boxes. Okay, so if you look at the stuff up to the first divider, this goes in box 1. So there are 2 bananas in box 1. Between these 2 dividers, that's box 2. Okay, so there are no bananas in box 2. Here is box 3. There are 5 bananas, 1 banana in box 4, and 2 bananas in box 5. Okay, because you don't care about the order of the O's doesn't matter, right? Because they're all the same bananas. It's just the quantity of the bananas that matter. Okay, this will suffice to be a mapping of one possible world state where so and so gets this number of bananas. All the bananas are accounted for. Okay, they've all been handed out. Okay, but this ends up being a mapping onto binary. And all you have to do is count the number of arrangements of this binary, and you got the answer. Okay, and that's it. And that's a problem that you know how to solve. How many different arrangements are there of this binary? Not 14, but 14 choose 4. Yeah. Okay, or 14 choose 10. Okay, so either way, select the positions of the zeros or the selections of the ones. I'll go with what you suggested, 14 choose 4, such binary sequences. Okay, so 14 is the total number of objects, and 4 is the number of dividers. I recognize a few of you in the room. You took Macam from me, and that's great. Welcome back. I always shuddered when I got to bananas and lunchboxes in Macam, and I wrote down the generalization, a fourth formula. The reason that I don't write down, or I don't like writing down the fourth formula, is because it's very difficult to figure out which one are the bananas and which ones are the dividers sometimes, and it's very easy to get it wrong. You end up with an off by 1, and that will just kill your answer. Okay, so I'm not going to write down the fourth formula. I'm not going to do that for you, but I'd like you to think about what the fruits are and what the dividers. Map it onto the binary. You'll never go wrong. Okay, never, never, ever, ever go wrong. Okay, if you're ever faced with a problem like this, there won't be a lot of problems like this in Compute 210. I'm mainly doing this for completion, but there is one problem of this type on your current assignment. Okay, so if you intend to do that one, you're going to need this. Okay, questions about the vanilla bananas and lunchboxes problem before we go on to the variations? Yeah, is it good? It's pretty cool, right? Just map it onto binary. Box 2 has no bananas. Yeah. Is it possible to have 4 ones next to each other? Yeah. Then one box will have all 10 bananas, and that's a perfectly fine distribution, right? I mean, maybe the people aren't going to be very happy, but that is one possible distribution. Okay, so that's one possible variant. I think you're sort of getting at here, and that is, you want to make sure everyone has at least one banana. So suppose each lunchbox must contain at least one banana. Okay, so that's to make sure no one goes hungry. What's the approach here? What should we do? Put one banana in each box and then? Good, so you do the same problem with 5 fewer bananas, right? So you sort of nail one banana in each, well, maybe nailing bananas is not the best thing to do. But you commit a banana, commit, we'll use commit. Okay, so we commit 5 of the bananas in advance and then distribute the remaining 5. Okay, so the total number of O's will go down by 5. So we'll have 5 O's and 4 1s. So 9 total objects and 4 dividers. So 5 O's and 4 1s. Okay, last problem. And this is the bananas and lunchboxes problem, believe it or not, as well. Okay, so in equation math, sometimes you're asked to do, solve an equation. This equation is, it hasn't got a lot of determinism in it, right? If this was a real value problem, you'd say there's an infinite number of solutions, give me a better problem. But here, they're integer solutions, right? So it's constrained to integers, and they can't be negative. Okay? So in this domain, and you might think of it as bananas and lunchboxes. One other thing I like to think about is you have 40 loonies, and you have 3 UNICEF boxes. And it's how many different ways are there of putting the loonies? You can only put loonies one at a time, right? You can't cut a loony in half. Okay, so, well, maybe you can, but, it's kind of difficult. So how many different ways are distributing dollar coins into 3 different boxes? Okay, or bananas and lunchboxes, right? There are 3 boxes in which you're going to put increments of 1 into each of them. Okay, increments of 1. Okay, so it's a bananas and lunchboxes problem. Okay, so 40 bananas. I think this blue has had it. And 3 lunchboxes. Okay, so that'll give us 40 zeros and 2 dividers. Okay, so 42 total objects. Choose 2. Okay, so that many different ways. Interesting that there's a finite number of solutions, and you can get at them real quick. There's another variant. You might see this in a textbook problem. Okay, instead of equal 40, it's less than or equal to 40. Okay, which means that you can distribute up to 40 bananas, right? What would you do here? Any ideas? Good, yeah. So it's almost like you have an extra lunchbox where you can put the remaining bananas. So and you can turn this into equality. Okay, so you add the extra. Oh, sorry. Add the extras lunchbox. Okay, so everything is left over there, goes into there, and then you have 4 lunchboxes instead of 3. Okay, so anyway, that's it. We're off.